Welcome to the second video on vectors. They're back. Let's catch up from what we were doing in the last video and then we'll move forward. Okay, so at the end of the last video, we were saying you should be able to add any two vectors that I give you, like vector A and B, together, and you can add various lengths of them. So again, these two values, P and Q, I could make them 1/2, I could make them 2, I could make them negative, and so they'd go in the opposite direction. But I can add these two vectors together and get to various places within the plane and to a specific place if I want to. So let's refresh our memory. So I've got A and B, and what I'm saying is how can I manipulate the lengths of A and B to end up at vector C when I add them? So, okay, so first of all, we're going to replace vectors A and B with those actual values, which would be 4, 3 for A and negative 2, 7 for B. And I want them to result in C, which is 10, negative 4. So how do we do this? Well, we broke it up into the X and Y components. So if I just look at the X components, it would be 4 times whatever the P value is, minus 2 times whatever the Q value is should get me to 10. For the change in Y, 3 times my same p-value plus 7 times q should get me to my y value change, which is negative 4. So now I need to solve these two equations. I'm going to, let's see, I'm going to multiply this first guy by a 7 and this guy by a 2, and that will allow me to use elimination to solve. So I've got 28p, they don't always come out nice. So I've got 28p minus 14q equals 70. And then times 2, 6p plus 14q, that was the whole point, equals negative 8. So let's see what we've got here. We've got 34p equals 62. So then I'm going to go ahead and do 62 divided by 34. I'm going to leave it as a fraction, as you should. And so I end up with p would have to be 31 over 17. Let's get q. So if I was going to do q, then I would plug this p-value back in. So I guess I'll just choose the first equation to plug it into and solve. So I'm going to do this times 4. Oops. This times 4. I'm going to subtract this from both sides. I'm going to do 10 minus that value. I get 46 over 17. I'm just using my calculator. Math the frac button, dividing by negative 2. So I get q would be negative 23 over 17. So there's the two values that you could use. Okay. So that's what we talked about at the end last time, these vectors and you know, being able to add them. Okay. So only a lunatic would choose any independent vectors if you wanted to try to be able to pick, you know, to move in space. Because like, for example, A and B, clearly it's not nice to move. Like I had to make them very weird things to get to C. So can you think of two vectors that I could add together? You could pick any vectors that you want. If you could put any two vectors to start, how would you make the vectors originally so that it would be easiest to add them and end up somewhere in space? You can pause it if you want and think about two vectors. Remember, you can have them go in any direction that you want, but the whole idea is that when I add them together, I can easily move around. Okay, hopefully, maybe you came up with this idea of going one in each direction. So like one in the x direction, and my other vector could be me going one in the y direction. Why would that make it so nice? Well, then I can easily get to places. Like if I wanted to get to, you know, 3, 1, then I could just go 3 in this x direction plus 1 in that y direction. You see what I mean? It's the p and the q are much easier to figure out because you're not moving at a weird diagonal way. So I guess what we're saying is here that we would like it to be just a strictly horizontal movement of 1, and then one vector that's a strictly vertical movement of 1. Okay, and that's exactly what mathematicians thought too. They said, why don't we make these vectors special so that they're only 1 long? And we gave them names, they're so special. Okay, so we call these basis vectors. I actually have a little bit down here. We call these basis vectors. And so we call the one that moves in the x direction by 1, we call that I. This is not the same as imaginary I. And we call the one that moves in the y direction 1 unit j. And so then that allows us to easily move around in our coordinate plane. So again, for example, if I wanted to get to the point 5, 7, which would be the vector 5, 7, same kind of idea here, then I would want to go 5 in the x direction plus 7 in the y direction, or look how I can write this, 5i, 5 in the x direction plus 7j, which is 7 in the y direction. So this is that new idea, this new basis. This is called, again, basis vector form. It's different than component form because it splits up the two components and he has the I and the J attached. So it's basically splitting up the horizontal and the vertical movement. Okay, this is called a basis vector. Eventually, when we get into 3D, we'll have a Z part to that, and the basis vector for that will be K, but we're not quite there yet. Okay. So then if you want to add or subtract vectors in basis vector form, it looks a little more algebraic. So, okay, so let's say I had two vectors, 3, -8, and, -7, 10. And I wanted to add these two vectors together. This is component form. If I change them into basis vector form, this is how they would look. That is a vector right there, guys. Plus, here's your second vector, -7i plus 10j. These are two vectors. That's a vector, that's a vector. So if we wanted to add them, you're going to add them just like you would like terms. So I have 3i minus 4 or minus 7i. That would give me 4 in the I or x direction. -8 plus 10 would give me 2j. So here's your resultant vector in basis form, or you could think of it like this, same thing. So this becomes what looks like an algebra problem, but it's still vectors because you are still looking at the movement. It's just, again, this is split up into the horizontal and the vertical part. Okay. Okay, so sometimes we do write basis vectors. They'll put a little vector on top of the I and the J. So you will see that sometimes. Sometimes they do, sometimes they don't, but they'll put a little vector on top, just to let you know that that is a vector there. So if you see that, just don't forget that. Again, we call these the components. You guys have seen all that already. And we can multiply it by scalars and stuff. Okay, so let's try some. So if I give you the points P and Q, and I want you to write the basis vector form for, this is vector PQ. I know it's hard to see that harpoon, but it is going from P to Q. So make sure we're trying to find the change to go from P to Q. Okay. Well, I'm going -7 in the x direction, and -2 to get to 7 would be a change of 9 in the y direction. So I would say, using the vector form, I would say -7, make sure you have the little harpoons on top, -7i plus, I went 9 in the j direction. So make sure those little vectors make it there. Okay, that's it. So there's your little basis vector form of going from P to Q. Again, it's a lot like component form, but I'm attaching the horizontal and vertical movement vectors to it instead. Okay, let's see. You can do scalar multiplication. So by the way, if I wanted to take if I wanted to take a third of vector PQ, so if I wanted to go in the same direction but only go a third of it, you do this the same way I did for component form. So I would just take a third of each of these pieces. So like my new vector would be -7/3 in the I direction plus 3 in the j direction. Same thing. So none of that scalar multiplication has changed. Okay, so the very last section of the chapter, we start talking about how do we write the equation of a line, which you guys know a lot of different ways to write a line. Like you guys know y = mx plus b form, which we talked about, in the last unit, last couple of units, standard form at this point. So like this one, let's see, this one's standard form would be 5x minus 4y, I think, equals -12. right? I mean, there's standard form. And then you guys also did parametric form, if you remember. So that's where we would have like x equals y equals. We'd have our starting point, you know, our initial x value, our initial y. And then we'd do our change in x over change in y times d, like we did that kind of stuff. So you've seen these different equations of a line. Well, you're going to learn how to do a vector equation of a line. And so it's going to give us a way to use vectors to get to various places that we want to be on that line. All right, let me get a blank page here because for this, I really like to show it by building it. Okay. So, all right, let's start with a vector. So I'm going to go out to 2, 1. We'll call that point A. And then I will go 1, 2, 3, 4, up 3, B. Okay. So point A was at 2, 1. Point B was at 6, 4. Okay. And what I want is I want a vector equation of line AB. Okay, so I want a vector equation. Okay, so how do I do this? Okay, so the first thing that we're going to do to create this line is we need to start by getting out to A. So we need to go from the origin out to point A. So this is its own little vector. So I want everyone to see that. I'm going to start by going from the origin out to point A, which is a vector. So here I go. So I'm going to start at the origin. That will get me to point A. If I wanted to move from now I'm at point A, right? Because I went from the origin out to A. If I wanted to get to point B, how much would I have to add to what vector would I add to OA to get to point B? I would add vector AB. Do you guys see this? This would get me to point B. Okay. What if I wanted to go twice as far along that line? Like what if I wanted to get out here? We'll call that point C. Well, then I would go out to A from the origin because you have to get out to where you're starting. And then I would go, if I wanted to get to C and C was twice as far, then I would add 2 of AB. Okay. And that would get me to point C. What if I wanted to get to a point, like let's say, because here's the line. This is the line that we're trying to write the equation of, guys. What if I wanted to get to a point that was like maybe back here, and maybe it was twice as long as this, but back this way? Could I get to this point? Sure. Go out to A first to get on the line, and then go twice, but in the opposite direction. So I could go -2. So I hope that you're seeing, I'll call this D. So I hope what you're seeing here is that I basically can go, once I get out to the line, I can just go various lengths of AB. And that is a vector equation of a line. So if I want the vector equation of line AB, I need to start by getting out to the line. So I need to go from the origin to the initial point. So I'm going out specifically to A. So I'm going to do that. Then you're going to go in various lengths of your vector. So then I'm going to add to that various lengths. So let's see what that looks like. I'm going to go from the origin out to one of the points on my line. Then I'm going to use T because I'm going to go various lengths of the vector that is on the actual line. So again, first I get out to the line and then I can move various lengths of that. And as long as T is any real number, guys, as long as you use every length, you're going to get every point on the line. This right here is your vector equation of a line. So let's do it specifically for this problem. So if I wanted specifically to do it for AB, I'm going to start by getting a vector that would get me out to A. So literally from the origin to A is literally just the point, 2, 1. Okay? Plus T, various lengths. Now I need to know, well, what direction does my line go in? My line goes in the direction of 4, 3. 4 in the X. So I'm just finding what vector AB is, guys. That's it. There you go. So then if you plug in various T values, you'll move along that line. Like if t is 0, let's see where that would get you. Think about that. That means that you don't go any in this direction. It would get you to 2, 1, or A. That should make sense. If I go 1, then I would go the full length of AB. So where would that get me? 6, 4, or it would actually get me to B, which should again make sense. If I plug in 2, then that's going to get me to a point that's twice as far. So I would multiply this by 2, so that would be 8. So 2 plus 8 is 10. And then I would multiply this by 2, that'd be 6. So 1 plus 6 would be 7. Again, if you want to go this direction on the line, then you just have to plug in a negative t value. Okay. So, all right. So for vector equations of a line, again, you're going to do, you have to figure out, what the actual change is of the vector. And then you're going to have to get out to your line and then solve from there. Let's see if I have more on here. I'll just do another example so you guys can see it one more time. So let's say that this is PQ and I want the equation. Notice I'm using line. I want the equation of the line PQ. I have options. I can go out to P or to Q, but I have to first get out to my line. I'm going to go out to P, that as the vector from the origin, which is easy. That's just a position vector. And then once I'm out there, I'm going to move in the direction of vector PQ, and that's going to get me that line. So I'm going to say plus various lengths, oops, let's keep it orange, plus various lengths t, that's your parameter, of PQ. So see, so then I'm going to add various lengths. Again, I could go half the distance and that would get me this point. I could go the full distance. I could go 3/4. See, if I do all the various lengths, positive and negative, I get all those points on that line. Okay, so this should look kind of familiar, like this idea of adding various lengths in a particular direction. Yeah, you've done this before, guys, in terms of like parametric equations. You're just adding this idea of a parameter. So this shouldn't actually be that new. What I've got up here, here's my vector equation of the line. Here it is in terms of basis vector form. So you could also do it in basis vector form, but you don't have to. So if we did parametric equations for a line, let's go back to remind yourselves of this. Parametric equations where x equals, you would start at the initial point. Then you would remember we have to do change in x over lambda, because then that way this would be a movement of 1. This was your, C1 times d. And then the same thing for the y value. Let's look at that compared to what we just did for our equation of our line. Okay. The t parameter that we chose for our line, so like let me get that line back up here. When we did a line, we went out to the line. You could start at any point, but I start at the first one, and then we're going to go t in the direction of AB. But the thing is, this t right here that you use is not like, if I want to go 5, I don't get to just plug in 5, because remember, this t is giving you how many lengths of AB you go. Like if this is AB. If I let this be 2, t equals 2, I don't go a length of 2, I go 2 of those, right? So if we want to go a particular distance, we have to figure out how long this is first, scale it down, and then we can go our desired distance. So this is a big deal. Make sure that you get this down. This parameter in this equation is like, I can't just plug, if I want to go 10 units, I can't just plug in t equals 10. I have to think of it as, oh, I want to go 10 units. Well, let me divide by lambda, which remember, lambda is the magnitude of the vector. So first you have to divide down and scale it to 1, and then you can go however long you want. Okay. So again, this is just me saying, if I want to find a point on D that is 5 times as far from A, we have to make sure that we're scaling things down first to actually solve that. Okay, so let's try some. Let's do one together to end this video. So let's say that we want to write the equation we want to do line CD, and let's make point C will be -5, 4, and maybe D will be 2, 8. The first thing that I would do for these would absolutely be to sketch it, just so you can see what's happening. So here we go. So -5, 4. So there's C, and then D is 2, 5, 6, 7, 8. There we go. So here is our line. This is the vector, but technically that line does keep going, guys, forever and ever and ever. Okay. But vector CD is on the line. Okay, so if we want to write let's start by writing the equation of the line in vector form. Okay, so the vector equation of the line would be, and here's what you can say. You can say xy equals. That means that, yes, you get a vector, but technically you're getting points on the line. You could also put CD here, same idea. Okay, so we need to get out to the line. Again, if I call it CD, I tend to go out to that first point that's listed, but you could go to D, but I'm going to go to C. So the first thing I need to do is get out to C, which would be from the origin out there would be just to go to the point. So there I am. This is from the origin out to C. Plus, then you're going to go various lengths of CD. This is giving you the direction you want to go now that you're out at C. So the direction I want to go, well, let's see. I got to figure out what vector CD is. Change in x, -5 to 2 is 7, and 4 to 8 is 4. Okay. Okay. So there's the vector equation of the line. What if I wanted this in basis vector form, right? That's a little different. So what if I wanted it in basis vector form? The first thing that I could do is switch this to -5i plus 4j plus t times 7i plus 4j. And then what you'll see sometimes is like people will group the i's together or the j's together, but same idea. Okay, that's basis vector form. This is component form. I'm fine with component form, but you should recognize basis vector too. Okay, so let's do some of the things that we did in the last unit. What if we want to find a point on the line that is twice as far? Well, that's actually hard. Let's start a little easier than that. Find a point that is, I'm going to try to pick one that's nice here for us. That is 3 root 53 from C. Find a point. I meant to say on the line. So find a point on the line that's 3 root 53 from C. This is something that we did in the last unit when we did equations of lines. Okay, well, it would probably help us to figure out, remember, if we want to go a particular distance and we want to figure out that t, we need to take the distance over the lambda, which is the length of the vector. So the first thing I need to do is figure out the length of the vector. Remember, this is just the magnitude. So I need to figure out how long CD actually is. So let's get that. Magnitude of CD is 7, 4. So I'm going to do 7 squared plus 4 squared. Probably can see why I chose what I chose. So the length of this is root 53. So what you can think of is, okay, well, I want to go 3 root 53. My lambda is 53, which basically means I just need t to be 3. So, okay, so then you could plug in 3 to your equation. So let's do that. So if t is 3, then that would look like my xy point would go -5, 4 plus 3 times 7, 4. Okay, and so that ends up giving me -5 plus 21, so 16 for the x, and then 4 plus 12, 16 for the y. How about that? Total coincidence. So if you wanted to write this as a point, though, all you have to do is change it to a point. This is just coming from the origin. Okay, there's actually another point that's 3 root 53 from C. I could go this way or that way. So I could also let t be -3. So if I do that, then I have -5 minus 21. So I would get to -26, and then 4 minus 12, which would be -8. So there are my two options. Two things actually work there. Okay. All right. I could obviously pick one that's not as nice. What if I wanted to find a point on the line? I'm going to make it a little easier in certain ways. On the line in the direction of CD. So it has to be going in that direction. That is 5 units from C. Okay, well now it's not so easy because I want to go 5, but my magnitude is root 53. So this is nasty, but that's what you would have to plug in. So then I'd have xy equals negative 5, 4 plus 5 over root 53, 7, 4. Ugh. So I'm just going to get, I'm just going to get a nasty answer here, guys. So the x value would be negative 5 plus 35 over root 53. And the y value would be 4 plus 20 over, it's just not going to be nice. I could ask you to just give me a decimal if I wanted to, but you get the idea. This actually came out nice because of its relationship to the magnitude. This did not come out nice because 5 wasn't a nice relationship to root 53. Okay. Now, we also did some ones where we would say, like, find a point that is twice as far from D as C is from D. Okay, so we want to find a point on our line, and we want that point to be twice as far from D as C is from D. Okay, so, well, you can think about it. C is from D is lambda, so that's nice. And we want a point that's going to be twice as far, careful, from D. Here's D. So I need this distance to be twice what this was. That's a little tricky. We'll call this point E. Let's think about that. How far would I need to go from C? Again, I want this to be 2 times that. So basically, you want to go, if you want to be twice as far from D as this is, then you want to go a total of 3 of those. I hope everybody sees that. I want to go 3 of these vectors. So that one's actually kind of nice. You're just going to let T be 3 because you want to go 3 of those lambdas is how far you want to go over lambda. So it's just 3. And then we've already done that one, so I'm not going to do that again. Okay. So that's how I can then start moving along my line. You're going to do some interesting things where we talk about, like, okay, what if I told you you had an equation for a line? So I'll do a quick pick here. Here's line FG. Well, excuse me, here's vector FG, but imagine it is a line, so it keeps going. So if you had line FG, what if I told you that your t value could only go from 0 to 1 instead of being any real number? How would that change what this is geometrically? So again, if you started with the equation of the line, and so you said, like, that would be like OF plus T times FG. Oops. I don't know why I wrote it like that. Let me do that again. Plus T times FG. If I let T be anything, then it would make the whole line. What if I only let T go from 0 to 1? Well, if T is 0, then that would just get you, that you would stay at F. If T was 1, that would move you the whole length, which would get you to G, and I can be anything in between. What is that? It's not a line. Yeah, it's the segment from F to G. So just, you can manipulate that if you want a little bit. We can also talk about lines being parallel. So, like, let's say that this particular equation, I'm going to give it an actual value. Let's say to go from O out to F is like negative 2, 6. And let's say that F to G is like 5 in the x direction and negative 2 in the y. Okay, so something like that. So let's say that that is the equation of that line. If I wanted to make a line, because we did parallel and perpendicular stuff, if I wanted to make a line that was parallel to FG, but went through the point maybe 5, 0, think about how that would change this equation. What is the only thing that would change? Well, your initial point that you'd want to go out to would be 5, 0. So you could change your initial point to 5, 0. How about the direction you want to go in, which is what this is? This is telling you the direction of your line, basically, guys. Well, if it's parallel, you'd want it to be the same. So you would keep this 5, negative 2. So again, you'd only have to change the line the point that you went out to. What if you wanted to be perpendicular to your line? You guys should know, well, we haven't necessarily talked about perpendicular vectors yet, but you could think about it as far as slope. So let's keep the initial point the same, but this time we want to be perpendicular. We're going to touch bases on perpendicular vectors a little bit later, but if you want to be perpendicular, you guys know, like if you're changing x and changing y, if your slope is 5/3, you want it to become -3/5. So you basically need to switch your change in x and change in y and switch one of the signs. So if you think about it, it should make sense. We'd go out to our initial point that we want to go through, but then we'd want our change in x and change in y to switch places and one of them to change sign. So I'm going to switch the sign on the -2 to a +2. So it's a little hard to read. There you go. And so that would be perpendicular. So we're going to talk about that a little bit. You'll see. Okay. So there's some parallel stuff, some perpendicular stuff. You'll get to talk about those a little bit more as you go through them. And yeah, good luck.